to amazing science to come. So Rubin Observatory is all about bringing the night sky to life. The NSF DOE, that's National Science Foundation and Department of Energy, jointly fund the Vera Rubin Observatory. We plan to revolutionize the way that we explore the cosmos. And this is a picture of Rubin Observatory on its mountain. The Rubin Observatory is located in Chile. It's on Cerro Pachón in the Coquimbo region of Chile. That's like just outside of La Serena. And it's right on a peak next to the Gemini South Observatory and next to SOAR. And it's sort of, one mountain over from Cerro Tololo where CTIO is. So lots of other observatories in the region. As I mentioned, we're jointly funded in the US by the NSF and also the DOE. We are named for Vera C. Rubin. She was a cosmic trailblazer. Her work provided the first convincing evidence that dark matter existed, and she was also an advocate for women in astronomy. Rubin Observatory is the first major US observatory to be named for a woman, and we're very proud of that. So we always use like the full name. You'll always hear me say Rubin Observatory or just sometimes Rubin when I'm referring to the observatory. We never use the acronym for that reason because we're very proud of Vera. So Rubin, I've worked with Rubin Observatory for 10 years now. It's sort of 10 years at the start of March. I think when I first started, we thought that the telescope would be ready and we'd have our survey started within, 5 years or so. But 10 years and a global pandemic later, we are finally getting started now. So in late 2024, a little commissioning camera went on the telescope for a little while, and then it came off. It helped to sort of commission the telescope as a telescope. And then in April of 2025, our big camera went on, and it took the first few images, did a nice little survey so that we could have a media announcement that Rubin Observatory was basically up and running, the camera was functioning, and we could share our first images with the world. So that's what I want to do just to start out the talk here. These are some of the first images from Rubin Observatory. This one is the Trifid Nebula, very beautiful. And this is one of our deep fields. And I just have a couple of more examples of some zoom-ins on these deep fields where you see Rubin Observatory can really bring out the low surface brightness features, tidal streams, bridges between galaxies, lots going on in these. And one of the things that struck me the most about these images was the color information that we're getting. The Rubin Observatory and its camera, it's got 6 filters in there. So you're getting a lot of information in every image that you take and when you put them all together. And I thought these images were particularly, these were made with a very custom pipeline to create very specifically beautiful color images that conveyed sort of the depth of information that Rubin is bringing. If you want to see these for yourself, you can visit skyviewer.app. That's like a publicly accessible way to access these images and look around. And aside from the beauty, one of the things that you can't really see in these images are the asteroids. In this particular image, when the stacking was done, the asteroids were left in. So like instead of a median combine, you can like use, I don't think they did this, but you could use a sum combine so that the little asteroids that are only there in one of the images that you've stacked remain in your final color image. And you can see them here where we've done like images in like R filter, green filter, green filter, green filter, blue, blue. And you see the little asteroid has moved along in the time that it took to take those images and change the filters. And you can see them show up in this images with the little trails there. And if you want to see a different view, so if you are a solar system person, then orbitviewer.app, you can go in and sort of do a 3D scan and see where all the asteroids that Rubin detected with its first look images are. And if you want to see more, that's all at our website, which is rubinobservatory.org. So you can go there, browse all these images that I just showed you. There's some really nice animations of like asteroid detection and that kind of thing, all there. There's also, I'm not going to play the full video because it's about like 7 to 10 minutes long, but we've had a documentary filmmaker sort of studying, observing, filming Rubin for the last maybe 8 years or so. And Allison Rose is her name, and she was on the summit the night of the first image with the big camera. And she made this really nice video that kind of takes you into what it was like on the summit that night. So you can watch everybody sort of getting ready for the night, and then it gets dark and they take the first image, and it's a really wonderful little video. So you can find this on Vimeo. I'll make sure you have these slides after. Maybe if I send them to you, you can and then you'll have the links. It's just a really nice little video that kind of introduces you to Rubin, the people, and what it was like on night one. All right, what are we going to do with this telescope that we've built? So Rubin Observatory will do the Legacy Survey of Space and Time. That's what the acronym LSST stands for. And what it's going to do is repeatedly scan the southern sky once every approximately 3 nights. So because we have such a big camera, we can cover about a third of the visible sky every night. And so then after 3 nights, we've covered all that we can see, and then we go back and do it again. And again and again and again in the 6 different filters over and over for 10 years. So we are ultimately conducting a wide, very, very wide field, all sky survey, not all sky, but like all of the southern sky that you can see from the telescope with the 6 color filters. It's U, G, R, I, Z, and Y, somewhat similar to the SDSS filters, if you're familiar with those. And then while we're building up the amazing depth that you get by stacking everything from 10 years, by spreading it out over time, we also build a very detailed time-lapse view of the cosmos for time domain astronomy, supernovae, moving objects, all of that kind of stuff. This is what the survey footprint looks like on the southern sky. So most of that green area that you see, that's getting 800 visits total in all of the 6 filters over the 10 years. And we refer to that as our wide, fast, deep survey region, kind of the main region. You can see a bunch of other regions are purple, and they're getting more on order of 1 to 200 visits over the 10 years. Those are mostly the galactic plane, where it doesn't make sense to spend a lot of time there. You can only build up so much signal before you're confusion limited because of the stellar density is so high. So those regions get a lot less visits, but we do cover them. And then you see the north ecliptic spur there, and the reason for that, covering that going into the north, that follows the ecliptic, so that's where we're getting a lot of solar system objects from. And so we cover that, but it also doesn't need the same number of visits over 10 years to find all of the asteroids in that region. And then also the South Celestial Pole spends a lot of time at higher air masses from our telescope, and so we spend less time there as well. So that's the green and the purple. And then you can also see some yellow regions in there that get way more than 1,000 visits over the 10 years. And those are our deep drilling fields. Each of those fields is about the field of view of the camera on the sky. And what you do in these fields is for one night, you go to that field, you spend about an hour there, and for example, just do GRIZ filters over and over again for an hour. And that gets you 2 things. One, you can make a deep image from that night by stacking up all of the images that you got of that one field. And then that helps you to find like fainter time variable things, fainter supernovae, higher redshift supernovae, because you've built up a deep image from that night. And then also because you took many, many images over and over of the same field, whereas usually we switch fields in the green areas. Anything that changes brightness really quickly, so flaring stars, it helps you find sort of fast-moving asteroids, although the area is very small, so that's not really the motivator. But you get really good sampling on any supernovae or transients that are in the field. So that's why they're called deep drilling. It's you're going really deep in a night, and also you're drilling on the field to get the time domain cadence in those small areas. This sort of map of the sky, and also all the decisions about the cadence and how basically the whole strategy of the LSST has been developed in tandem with the scientific community. So Rubin Observatory basically starts by saying, I think, this strategy would be good to hit all of the science goals that we want to do. They make a simulation of the 10-year survey, so all the pointings and the filters that they're going to do, and then they hand that simulation over to the community, who goes off and analyzes it and says, well, actually, this doesn't get enough U-band visits for our supernovae, and our supernova light curves are undersampled, so you should do it with more U-band. And then Rubin goes away, takes everybody's desires into account, comes up with a new strategy, sends the new simulation back to the community. They do the same thing, give their feedback. And we've done this 5 times now, back and forth. And we've finally landed on, and this is the footprint. And we have a strategy for example, how many visits per filter get observed over year 1. So this is called baseline version 5 survey strategy. And it's what we're going to go with when we start the first year of our survey. So the motivation behind building this observatory, running this survey, like building the camera, doing the survey with it, can sort of be broken up into 4 main science areas. We've got Milky Way structure and formation. So Rubin will help us make the best map of our home galaxy yet. Dark matter, of course, because we're named for Vera Rubin. Dark matter and dark energy. Rubin is a brand new tool to help us learn more about dark matter and dark energy. Taking a census of the solar system, Rubin's going to find millions of new asteroids and comets and be able to like really fill out our inventory of the solar system. And then also the last one, the changing sky. So Rubin's going to bring the night sky to life because we're observing over and over again. We find all the transients and variables, a treasure trove of new discoveries in the time domain. So just to go into some of these science areas in a little more detail, when we say changes detected in one Rubin image, this particular infographic gives you an idea of like the number of different types of objects that you get with just one pointing on the sky, which is about 9.6 square degree. That's a 9.6 square degree field of view. So in any given pointing, there should be about 200 supernovae, about 7,000 variable stars that change brightness over time, about 70 active galactic nuclei in every pointing, and about 400 solar system objects like per pointing. And that is one pointing, one observation is just 30 seconds on the sky. And then we're doing that over and over throughout the night. As far as the changing sky, so explosive events, this is my personal science area, is type 1a supernovae. So I know there's lots of cosmologists in the crowd, and you like the type 1a supernovae, and they're used for dark energy cosmology. I've always been very interested in their progenitor systems. We know they're a white dwarf that explodes, but exactly why or how that white dwarf explodes and what the role of the binary companion star is in that scenario, still some open questions there, and that's the aspect that I work on. I'm particularly excited because my thesis was looking at sort of the rate of type 1a supernovae in very specialized environments, like very rich clusters, or a radio loud AGN, or in starburst galaxies, trying to find different influences on the explosion of a type 1a supernovae. And for my thesis in these special environments, I only had like 2 to 8 supernovae in each of these special environments. And Rubin is going to give me thousands, which will be great. So one of my first to-dos is I want to try to redo my thesis, which was a null result. So if you are a grad student and you're working on your thesis, and if it's not going that great, maybe it's okay. My thesis was a null result. I couldn't really say anything about special environments and their effect on type 1a supernovae because I had so few objects, but it was a fun thesis anyway. So if you're a grad student, just keep going. Yeah, so I want vindication. I want to redo this with Rubin Observatory. For Milky Way and structure formation, Rubin's 10-year data set will create a catalog of Milky Way stars in unprecedented detail, creating a 3D map that's 100 times larger than previous surveys with data on billions of stars. And the Milky Way, of course, understanding our own galaxy is good for understanding galaxy growth and evolution in general.
When you say 3D map,
that came up in conversation the other day, and I meant to check our data products definitions to see what you're actually getting. I know proper motions and parallaxes are in there, but I couldn't remember if distance is like a planned column that we deliver, or if it's something we let scientists derive themselves. Good question. I'm sorry, I forgot to look that up. And so for the tidal streams, for example, this is not an LSST result, but it is a pretty amazing work. This is also, so Peter Ferguson and Nora Shipp are both at University of Washington, which is where I am. So often Peter wanders into my office with like amazing graphics that look like this with the new tidal streams that he's just found with DECAM. That's the dark energy camera. And so they're finding, once you go into great detail and you observe all sky, you can start to see all these streams around the Milky Way. And of course, LSST with its all sky nature and its very deep co-added images, you'll be able to find lots of tidal streams. And that tells you a lot about how the Milky Way formed. And also, I think you can do stuff with the dark matter of the Milky Way potential from that as well. For dark matter and dark energy, of course, since we're an all-sky survey that's going to create really deep images and also have the image quality necessary for like large-scale structure and weak lensing, you can look at the clumpiness of the universe, and that reveals, of course, where the dark matter is hiding. I don't understand, actually. So these slides, I should say, I didn't make these. These are from our EPO team. I'm actually not sure with how it interacts with dark energy, what that means exactly. I'm gonna have to follow up with our EPO team on that. But in addition to like large scale structure and galaxy clustering, gravitational lensing is something that's going to be also very excellent with Rubin Observatory. This is just an example of one strong gravitational lens in Rubin's first look images. But of course, again, since it's an all sky survey, with resolution that's better than previous surveys, people will be able to find lots of strong lenses in the LSST data. Looking again at the solar system, some of the big questions there that people are trying to answer by taking a census of the solar system is how do planetary systems form? And of course, how did we get here? And looking at all the small bodies in the solar system can tell you a lot about sort of how the planets migrated and moved about the solar system and how they formed. And in this particular visualization, the bright ones in here are the 11,000 asteroids that Rubin detected that were reported just back in April. So the solar system team is really going for it. They did a lot of detections when our first look images came out, and they've made several big batches of reports to the Minor Planet Center. And this is just visualizing like the latest haul basically from Rubin Observatory. And these, again, you can explore them using the Orbit Viewer .app website. For asteroids that pose a threat to Earth, this is also one of the main motivations for building Rubin Observatory in the first place. The census of the solar system is also a census of the potentially hazardous asteroids. And I think it was a mandate from Congress to NASA that something needed to be built to find all asteroids down to a certain radius, like maybe 100 meters or something like that. And so part of Rubin's mandate is to help NASA fulfill that goal as well and catalog all the potentially hazardous asteroids. And then, of course, the interstellar objects, which have been kind of a surprise over the past 3 years. So kind of hadn't seen any before, and then 3 in the past, I'm not sure, 5 to 6 years. The 3I Atlas was the most recent one, and it happened to visit us in July 2025, just a couple of months after the big LSST camera had just gone on the telescope. And it happened to be very, very close to one of the like commissioning fields that they were needing to observe anyway. So I think they just sort of upped that commissioning field a little bit over and got some data on 3I Atlas. And this was one of the first papers that came out. It's a Chandler et al. 2026 paper with the first data from Rubin Observatory, and it was for an interstellar object, which is just very, very cool. And the other thing Rubin will do, which is not actually part of the survey. So I showed you before, like the deep drilling fields, the wide, fast, deep, this whole survey was built for the 4 main science goals. But Rubin will also operate in target of opportunity mode due to its very wide field of view. It's an excellent tool for following up and looking for the optical counterparts of gravitational wave events. One of the best facilities in the world that can do that because of first the large aperture, so large light collecting area, and then also the large field of view on the sky. So yeah, Rubin has a target of opportunity board, basically, that is the one that decides which targets or like which gravitational wave events meet the criteria to be followed up by Rubin Observatory. And then all of this data, since it's going to be processed, I'll talk more about the processing in a moment, but it's going to be promptly processed in real time, and alerts will come out for objects detected in these fields. So this will be public data that comes out from the target of opportunity mode. Right. So that is kind of a very brief rundown of the very wide amount of science that Rubin is planning to accomplish. Or, I mean, Rubin's staff aren't the one doing the science. It's the science community who will be writing the papers and doing all of the science. We're just the ones sort of making it happen so that people can use the data. So all of this happens, and there's kind of three areas of what we call cutting edge technology that went into Rubin. The first is the camera that I've mentioned a few times, very large field of view. There it is for scale with humans. So it's physically a very large camera, largest digital camera in the world. It has like a Guinness Book of World Records certificate and everything for being the biggest camera, but 3,200 megapixels with those 6 filters. And then there's the telescope itself, which also has the name of Simonier Survey Telescope. Simonier was one of the early donors who helped the Mir get cast originally many years ago. And so the telescope is named after Charles Simonier. It's got a novel 3-mirror design that I'm going to talk about a little more that makes it like very sturdy. It's a very fast telescope, both in the sense of like the focal ratio, but also in the sense that it can move really quickly because it's so short. So it doesn't have like much of a settle time like other telescopes do. And then of course there's the global data management system. With this much data coming off of a massive camera coming off every 30 seconds, you need a whole system to deal with that. All right, so just to take a quicker look at the LSST camera, like I mentioned, largest camera in the world with 3,200 megapixels. It would take 400 ultra high definition television screens to display a single image, like with 1 pixel on the TV screen for 1 pixel from the camera. The field of view on the sky is about 45 times the area of the full moon, which you can see in this image right here. And then the 6 color filters, that's what these are here. You can't really, I mean, I think they're beautiful, but you can't really tell the colors from there. And just for a little bit of terminology, one of the detectors of the camera, it's a CCD, or we call it a detector. And then one 3x3 group of detectors is called a raft. All right, to have another look at the Simonier Survey Telescope. This is the first ever telescope that has a 2-in-1 primary and tertiary mirror. So what happens with the light path is it comes down from the sky and it reflects off the primary mirror, which is actually the ring around the outside that has one curvature, like carved out of this single piece of glass. The light goes off the primary up to the secondary, back down to the tertiary mirror, which is actually embedded with a different curvature within the same piece of glass that the primary mirror is on. And then back up into the camera, which is actually like in front of the secondary mirror. And these are just some of the initial camera optics that the light path goes through. And so to put that on the actual picture of the telescope, you can kind of see, I think like the M1 is here, M2 is on the inside, and you can see the hole in the center of the M1, M3 mirror. And up at the top, what you're seeing here is this is all the baffling around the M2 up at the top. So it's like protecting M2, the secondary mirror, from straight light. And then this right here is the camera sort of poking through the secondary mirror, which, yeah, that's where it sits sort of up at this focus. And you can kind of tell, so this is, I think, Ranpal and Kevin here. They're pretty far in front of the telescope. So it's a very, very large, imposing beast. and it moves very, very quickly. So it's actually set on magnets, and there are capacitors that live underneath the telescope that supply the charge to like move the telescope really quickly and then slow it down really quick again. If you've done observing with any more classically built telescopes that are maybe like really long, and you sort of, when you have to slew them, they move so slowly, and then they slow down, and then you have to wait while they sort of wobble a little bit, and then they come to a complete rest, and once they're settled, then it's time to take the image. But with this particular strong design, it just sort of moves super quick, and it's just settled, and it's ready to go for the next image. So having this particular design makes the LSST survey possible. It really minimizes our overheads. So we're only spending maybe 2 to 4 seconds. I think it's 4 seconds total between image. Readout takes 2 seconds, and then the slew and settle is just 4 seconds between images. Okay, so as you can see here, telescope fully built, cameras installed. You saw the images. What is going on at the summit right now? We haven't actually started the 10-year survey yet. We've been in a commissioning phase for a long time. And one of the biggest challenges, and this is not my area at all, there are lots of very talented people who are working on the active optics system. But that is what's been going on up there, is engineering time being spent on the active optics system. So both of those mirrors, the M1, M3, and the M2 mirrors, have actuators on the back of them that correct in real time the wavefront aberrations over the full field of view of the telescope that are induced either by gravitational or thermal effects. So that primary mirror, the M1, M3, is like 8.5 meters total. And it's got a honeycomb design in the glass, which does make it quite strong. But even then, when you tilt the mirror over, it's going to bend and distort. And so you have to undo that using the actuators on the back to sort of push it back into the right, into the right shape. And then as the temperature changes over the night as well, that will also warp the mirror a little bit, that the actuators then counteract that warping to push it back into the right shape. So that happens on both of the mirrors, have actuators that can bend them to correct the wavefront. In total, that means the control extends over 50 degrees of freedom, and that's what's illustrated in these two figures, one for M1, M3 on the left, and then the other for M2 on the right. And these are all from Guillem's paper back in 2024. So you can kind of see that there's just a lot of things to figure out, a lot of degrees of freedom, and they're still sort of building up the models of like what you tell the actuators to do in order to correct the wavefront that's coming from the telescope. And that's been a very active area of work. But the message is that things are getting better. So what you're looking at here are plots of the estimated system contribution. So the optics, the AOS system, basically end-to-end system contribution to the image quality. That's the red line, the red distribution in each of these plots. And what you're seeing is our science validation surveys from last year, all of early ops, so that's like all the observations that have been taken so far, and then recently. And the point is that the distribution of the estimated sort of system contribution to the image quality is both tightening up and shifting towards lower values in arc seconds. So this is basically like the full width half max in arc seconds that is being introduced into our point spread function of our images for our image quality, that is due not to the atmosphere, but to the system. And the green, areas that may just sort of look shaded, that's our target. So we want to get the system contribution to the overall image quality below about 0.4 arc seconds. That's like right about here. And you can see that for the first time in the last 2 weeks, they've managed to get that with like by calibrating the AOS system. So very promising that things are looking good. The AOS system can now like correct the wavefront and do it in a sustained way, which is what we need to start operations. I'm just gonna maybe pause. Do you want to do questions in the middle or at the end? Yeah, that was just a lot of information. Yeah, I thought there might be some questions. Oh, wait for the,
I have two questions. One is, what is the typical seeing at the site? Like,
yeah, I think what we expect a median of like 0.7 arc-second seeing once everything is working, right? Yeah.
and so you said 4 second from slowing from one position to another position, right? So
Mhm.
that's when you're going to an adjacent field, or it's for like a
Adjacent.
TO where when there is like some gravitational wave detection and you have to move to it. What's the typical time scale it
Yes.
takes?
So the 4 seconds is to go to the adjacent field. So it's just to move through like the 9.6 or like yeah, it's like I think about 6 if you go center to center. 6 degrees, 5 degrees. So that's how long. And then yeah, if you want to slew, like if there's a TOO and you're going all the way to the other side, it's something like, oh, I forget. It's on the website what our max speed is, but I don't like to quote values when I don't remember. It's pretty fast. It's pretty fast to go all the way around. Maybe 30 seconds to turn around. Yeah, the dome is the limit there, though, actually. The dome is slower. So if you're slewing up, then because of the way the dome aperture is, then maybe you can get there faster. But I think it's more like a minute or two for the dome to trundle its way all the way around. Yeah.
So, what is so the there have been many fantastic things in this design. One is of course the optics thing. So for this, the mechanical side, like how it can move and then not vibrate like any real telescope would, other telescopes would do. So, what was the key breakthrough which enabled that technology?
Oh, that's a great question. Um, I don't know if it was materials or design, or both, maybe. Um, part of it, part of it might be materials, whatever it's built from. Mm, but also the design, you can see how short it is. And so it really just doesn't have the length to wobble around. So yeah, I think design is probably the answer there. Yeah. Yeah, good. Okay. Does anyone else want to jump in on a question on like the science or the design? Yeah.
Just a related question regarding vibration. So Chile is quite prone to earthquakes, right?
Oh,
So
I can't actually hear you very, just say, I think just speak a lot louder into that.
so Chile is pretty prone to earthquakes, right?
Yes.
So how do you like take care of this? Because as far as I know, it's like very often and sometimes consecutive nights. So how does that affect? And I mean, like you have some extra protective system to save the telescope from this.
Yes, there is some extra protection and like isolation from the ground so that we don't suffer from the earthquakes. And you're right, there are like at least one a week up there. They're, yeah, very frequent. I don't remember exactly how it was built in. I just know they did do something special. Yeah.
Thank you.
Any more questions on design? All right, we keep going. Oh, yeah, go ahead. Oh, microphone, yeah.
The filter is probably between that lens and the camera, right? If you have 6 filters, I don't really space for storing those filters. Are they also stored in the primary, or they like the daytime you put it in the place?
Yeah, so the filter carousel holds 5. And so the camera is like this, and then the filters are sort of in 5 around. And so they rotate and then they slide in front. And so every 2 weeks or so, they usually swap out U and Y band for dark time and bright time. So the UV and the near infrared. So they change out those, and then the GRIZ are kind of always in there. So that's, yeah, that's how that works.
So is there like, you said that it's like it takes 3 nights to cover one sky.
Mhm.
So do you change the filter inside a night, or you just wait for the filter change to happen during daytime and then continue?
No, they will change the filter during the night. So one of the constraints from solar system observations is they do want 2 observations of the same patch of sky within a night, but separated by like at least 30 minutes. So that's one constraint on the survey strategy. And that can be in the same filter or in different filters, but is much better for everyone else's science, like transients, variables, if it's actually in a different filter. So they do filter changes during the night, and it's an order of like 2 minutes or so to do the rotation and change the filter. I think it's the max is like as long as it can take. So yes, they do change the filter sometimes during the night. Yeah.
Wow, that big filter moved into place in 2 minutes.
Yeah, actually, it's faster than 2 minutes, because when we do deep drilling, you want to do like GGG, so you want to be changing the filter more with deep drilling. I'd have to double check the timing for the filter change, but yeah, it's not nothing, but it's not so expensive that
These
they-
are like special dielectric filters that big, or it is like some glass?
I think they're glass, coated glass. Yeah, I think so. Yeah. Yeah.
Yes.
Yeah. Okay. I should aim to stop talking at 10 minutes too, to leave more time for question.
More minutes.
Yeah,
Good.
10 more minutes. Okay. All right. I'm just going to skip some things because I do want to talk. So usually when I give talks, it's like all about the data products, and I tell you about every single table and every single catalog and all of the columns. So this is actually a new slide deck that I'm working with. So I kept adding things because for this specific audience. So I do want to go a little bit into the data products that are coming, because these images that come off the telescope, we process them in real time. So immediately an image comes off, it gets instrument signature removal, like image reduction happens, calibrated, and then we take a template image that was obtained the year before, subtract it from the new image to make a difference image, and then release alerts based on differences that we see in the difference image. So of the real-time data products that we're putting out, alerts are one of them. Once we're sort of up at full steam, there will be 7 million alerts per night coming out of these images, and these get distributed to alert brokers. A single person can't deal with 7 million of these alert packets per night, but the brokers, I'll talk more about brokers, they handle those. And then also we have all of the information that gets streamed out in alerts also gets stored in queryable catalogs that get updated on 24-hour time cycles. And then all of the raw and processed images from the prompt processing comes out after 80 hours. So for the prompt products, that's what's happening. This is what I was talking about taking a new image, an older template image, and creating a difference image. And then you run source detection on the difference image, and any object that's changed in brightness between the science and the template will show up as a source in the difference image, exactly like this. For Rubin Observatory, we call something detected if it's detected with a signal to noise ratio greater than 5. That's basically the cutoff for all kinds of detections in all kinds of images. And then the alert packet itself is all the measurements that we make about this difference image source. So it's sky location, like the coordinates, the magnitudes that we measure for it, observational metadata, a 12-month history of past detections at the same location, which is basically the light curve, and then very small image cutouts. And these all get put together basically just in a little ASCII file. And it's one per source that we detect in a difference image, and they just stream out to brokers one after another through the night. So the alert stream, as I mentioned, could be up to 7 million alerts per night. That's a lot to handle. And that's what the alert brokers have been working on and building. They are independent software systems that process and serve the alerts to the community. And then as a scientist, you go to the broker and use their interface and their tools to get your objects of interest from the alert stream. Oh. Sure. Firoza? Oh, the hand went down, I think. Could type it.
On the topic right now, you can unmute yourself.
Thank you. Yeah, so I had a question, Melissa. This is Firoza Sutaria from Indian Institute of Astrophysics, and I want to know what templates are you using for the image subtracted transients that you've detected? Because at LSST's resolution, I think most templates that are presently available are at much lower resolution.
Yes, right now we're only using LSST images as templates, so they are matched in resolution.
Okay.
Yeah.
All right. So presumably your template stacking will improve as you have more and more data from LSST. Is that it?
Sort of. Actually, when you build a template, we will just be using data from the year before. They don't have to be that much deeper than your images. What you do want is to build your template out of images from the year before that were all the best seeing images. So
Yeah.
usually, your template that you build is from the year before, just as best seeing as you can make it.
Okay.
Yeah.
Thanks.
Okay, you're welcome.
Thank you.
All right, so these alerts go out to brokers, and then brokers are the ones that serve the alerts to the science community. This is just an example of what it looks like to use one alert broker. I picked the LSST broker, which is the one that's being built in Chile. They offer a wide variety of services. So if you do work in the time domain, brokers are where you go to get like interactive visualization of individual alerts or objects that were detected via the alerts. You can set up custom filters, watch lists for certain areas of sky where you want to be notified if something happens there. They do catalog cross-matching. They will run classifiers on both the image stamps and on the light curve to say, oh, this is probably a type 1a supernovae, or this is probably an AGN. They release probabilistic transient types, and they also offer data for download, plus a bunch of other stuff. So if you're doing real-time transient science, the alerts are where you will go to do that. And the alerts are now streaming. So as of February of this year, the LSST alert stream went online. The brokers had a bit of a commissioning period to make sure all of their stuff was working. And then we all went live together on Tuesday, February 24th. And now the community can access LSST alerts through the brokers. So if you are a time domain person, a good place to start is either rubinobservatory.org or in the prompt products documentation. So at one of these links, you can go and get started. Yeah. Say the question again into the mic.
Is there a already placed mechanism what science areas get priority, or there is some decision making which happens there? Because this has to be really quick.
Yeah, so alerts go out just as soon as we make them. And then it's the brokers will do some of them. When I say like custom filters, that means you can go in and you sort of write Python code to say, is this alert, does it have like more than 10 detections and is rising at 2 magnitudes per day, and it's blue if you take the GNR color. So you can like put constraints on it that say, oh, this alert is maybe like a young supernova that's in my interest. And then the broker can tell you about it, and then you can prioritize your follow-up based on the characteristics in the alert. Does that kind of answer your question? Yeah, okay, yeah. That's kind of the workflow for prioritizing follow-up. Right, so alerts are out now. The other types of prompt products that I mentioned should be coming online later this year. And then, of course, in addition to the prompt products that come out in real time, every year over the life of its survey, Rubin will reprocess all the data that it ever took with the latest versions of the LSST science pipelines and make a new data release that includes like the deeply stacked images and the measurements that are made of objects in the deeply stacked images. And then those become available on a yearly basis with a 2-year proprietary period. Just a few notes about the Rubin data policy. I mentioned the proprietary period is 2 years, but alerts are public. So there is this concept of a Rubin data rights holder. And so I think some of you in this room are Rubin data rights holders and you've been participating, and some of you aren't, and that's fine. So if you're not a Rubin data rights holder, there are a variety of ways to still participate in Rubin science. One, you can do time domain science with the alerts, which are public. You can still join some of the LSST science collaborations and work with other people who are also working on Rubin. And then there are ways to collaborate with your colleagues who might be a Rubin data rights holder. The data rights holders can share derived data products. So if they're going in and making calculations from the data products that you can then apply your models to, that's great. They can share the derived data products with you, and you can go off and write your paper together. If you're doing follow-up, for example, so if you have access to a follow-up facility, like to get spectra, and your colleague is a Rubin data rights holder, they can make the target list, so they can go into the catalog, find objects of interest to your follow-up survey, share the coordinates with you, you go off to the telescope, you write a paper together, that's great. Any other situation of co-authoring papers with Rubin data, completely fine. So not having Rubin data rights doesn't mean you can't like use the papers. It just means you can't like have full access to the images and catalogs. That's the only constraint. And then there's some public EPO data products that will come out if you're a teacher or if you're going into classrooms. You can use any of our EPO resources to do your work there. And then the post-proprietary data will also be served publicly, so far at least by the Canadian Astronomical Data Centre. So after 2 years, it becomes public and you can access it via other ways. So India's in-kind program right now has 36 named data rights holders, and these are basically the people to contact locally if you want to learn more about Rubin or if you're looking to collaborate with someone who does have data rights access, you can go to these people. So that puts us at 50 minutes. The rest of this is all very practical information about the data releases that we have coming out and the Rubin Science platform. I think I will just show you what's coming next, and it's this one. So I had mentioned there was a teeny tiny camera that first went on the telescope. So we made a teeny tiny data release last year that's just like a couple of pointings on the sky. That's a lot of fun, but this is what's coming this year. This we call it Data Preview 2. It's all images from the big camera, and everywhere where you see like a blue square, that's a helpix pixel that represents the number of visits that were obtained in that region of sky. And then wherever you see a little box, that represents where deep coad images will be coming out with Data Preview 2. So if you are a data rights holder, if you're looking to get started and test some analyses with Rubin data, this should be out between like July and September of this year. And this is sort of the next step. And the next thing after this will be data release 1, which would be based on the full first year of data, and it will be all sky. So we're slowly working our way up from small little areas to this bigger area to a much bigger area. It's all data access stuff. And then I'm just going to end here with just a slide of handy links. And very happy to take more questions about Rubin Observatory or the data, how to access it, anything you need.
Thank you very much for
Yeah,
the
thanks.
wonderful lecture.
Thanks.
Open for the question. Questions?
Yeah. So at the time of one observation, there's only one filter which is made available, right? And then, so for one epoch, I'll have only one filter information, right?
Yeah, one visit image is with one filter, one pointing, one specific time.
Oh, okay.
Yeah.
Hmm.
Yeah, so but you also mentioned that there will be another, so the solar system scientists want another visit within the same night. So does that mean for the same, does it mean for all the patch field of view I get another visit, or is it limited to some fields or something?
Yeah, so I think what will happen over a night, and I haven't delved deep into observing strategy, but I think most images will get a second image driven by the solar system needs for that, but probably not all of them. And I don't really know the fraction.
But you
that
also
will-
mentioned because like over 3 nights, the whole view will.
Oh, yeah, I think that quote takes this into account.
Okay.
Yeah.
Right. One more follow-up. So basically, like ZTF and Atlas, and they have this forced photometry server.
Mhm.
If I need a light curve of some source, it doesn't need to be in the source list of ZTF or something. I can just put the coordinates and get a light curve. is there a similar mechanism with the brokers that I get? Like, if I have RA and Deccan, I want to like.
Yeah. Not through the brokers. You can't do it there, but you can, if you're a Rubin data rights holder, use the Rubin Science platform to do force photometry at whatever sky location you want. And I should mention as well that every sky location where we see anything ever, we do force photometry in every single image at that location. So everything that we've already detected, you get force photometry in every direct image and every difference image, sort of for everything. So a lot of it's already done, but then if you have another coordinate, yeah, you just have to do it yourself.
But that will have to be through the data rights.
That would have to be through the Rubin Science platform. So right now there is no publicly accessible force photometry generator because you need data rights to access the images from which they're made. Yeah.
Makes sense. So, thanks.
Anyone else have a question? Okay, so you can unmute yourself, Firoza, and ask your question and then repeat with the other ones.
Yeah. The question that I had was about the LSST cadence. Is it been completely frozen in? I might have missed that part of your talk out actually. So especially for transient surveys, very distant supernovae, etc. I was wondering to given the depth that you would be able to go to, you might if you'd not have a frequent cadence of observations, you might actually miss out the young supernovae at high Z. So can you please say something more about the cadence of observations?
Yes, I could say a few things more about the cadence of observations. I think your first question was whether it will be frozen in, like whether we make.
Yes.
Yeah, that's a definite no. So the Survey Cadence Optimization Committee is a standing committee that's going to review the survey strategy regularly over the course of the LSST to make improvements so that we're doing the best that we can. So that is one thing I can say. And the other thing I can say is that what this particular plot doesn't show is rolling cadence. So at the end of 10 years, we do want uniform depth over the wide, fast, deep field. That's why most of it is green. But and in our first year of observations, we also kind of want to have fairly uniform depth so that our first data release uniform depth over the sky. But then starting in year 2, they're going to implement something called rolling cadence, where you basically divide your wide, fast, deep area into like a north and a south. And the north gets extra observations and the south gets fewer. So, and then in your year 3, you switch. Your south gets more observations and your north strip gets fewer. So that at the end of 3 years, you still have a uniform over the sky, but in between time, you've had a higher cadence in half your area, and that's much better for supernovae observations. You get a better sampled light curve for the supernova that you're detecting. And that is the current plan, as I understand it. Does that kind of answer your question?
Yeah. I was wondering how many days apart is the cadence supposed to be?
Yeah, so
With the single observation, you go down all the way till around 23rd magnitude in R, don't you?
I think a single observation is 24.5 in R band.
Okay, so that's extremely deep. Like you really are hitting the edge of the observable universe. So at least as far as transient phenomena at high Z is concerned, you just it's just a thought that maybe you might miss out the early part of the light curve. But on the other hand, you will detect more. So I suppose that's okay.
Yeah, so if you are going after very high redshift, very faint things, the other thing that I didn't mention is for the deep drilling fields, if it was a night where a deep drilling field is done, you can stack all the images for that night. And then you can also do difference imaging, provided that you've made a fainter template image. And then you can get much deeper with your transient studies in the deep drilling field. And that is something we should be doing and making available as well. So I think that would work best for your high Z transient.
Yeah, I think that would be the best thing. Yes. Yeah, great. Thank you. Thanks.
Yeah, thanks.
Professor Gopu, you can go ahead and ask your question and unmute yourself.
Thank you very much. It's amazing talk. I have a follow-up question on the tidal stream. So those data will be available during the data release, right? Because no, if somebody wants to create or refine the gravitational potential of the galaxy using tidal stream, I presume you have to wait for the data release and then work on it, right? That's the plan.
Yeah, I
Can
think
you?
you're right on that one. You would want to use you need to use the deep coad images from the annual data release. Yeah.
And that will be, I mean, so these images will be available for public, or this needs to again go through the, you know, people with the rights?
Yeah, the deeply co-added images in an annual data release are available only to Rubin data rights holders for the first 2 years, and then they're public after that.
Yeah, okay. Thank
Yeah.
you very much. Because this will be very interesting, because this is in the southern skies, where in the coming years, SKA will look for millisecond pulsars, maybe 2000 of them, and they can also map the potential. So there can be a very nice way of making comparisons and things like that. So yeah,
Okay,
thank
good.
you.
Yes, you're welcome.
Are there any other questions? Yeah, please.
Hi. So I don't know whether I understand it properly. The broker system is a like query-based system where you want to know which transients are in this part of the sky. So is there a mechanism where like transients, like major transients which are detected to alert the astronomical community to follow up in multi-wavelength observation?
I think I didn't catch your entire question.
So as I understood that the broker system is a query-based system where you ask that in this part of the sky, like if there are transients or not. So my question is there a mechanism where like if you detect a transient, like significantly bright transient, is there a mechanism to alert the astronomy community for multi-wavelength follow-ups?
Yes. So yes, there are ways if you're doing your own survey.
No, from the observatory side, is there? So since the difference images are being made like in every visit, so I was wondering if that is something which uh, LSST observatory is offering.
I'm sorry, I still can't fully hear your
So-
question. Just like speak.
Yeah, I am saying that whether there is a mechanism if you detect a transient,
Mhm.
okay, in a certain visit, is there a mechanism to let the astronomy community know
Oh.
that there is something and there can be a multi-wavelength follow-up of that transient?
Yes, sorry. That is the brokers are the mechanism for that. So all the detections from Rubin go to the brokers, and then they are the ones that have preset filters. So like if something needs follow-up or if something is likely a supernova, they're the ones that are like looking at the light curve and doing the classification. So if we have more time, I could show you, but you can go to sort of any of the brokers they're public web pages. So you can go and often just click around and say, show me everything from the last 2 days that has a photometric classification like a type 1A. And you can sometimes make a few other constraints. And then you get a list of all of the LSST objects that match your constraints. And you can do follow-up on them, classify them. And then there's the other step of like saying, I took a spectrum and this is a type 1A supernovae. We use a different system for that called the transient name server. That's where people are reporting classifications. But I think the part you're talking about is broker functionality. They're quite complicated and powerful tools that you just kind of have to pick one and try their website, go to their website, see what you can find and see if it works for you.
Okay.
Yeah.
Hi, Melissa. Probably a very naive question. why do you have 6 broadband filters? Why didn't you go for narrowband many filters?
Yeah, so I mean, I wasn't around at the filter definition time, but photometric redshifts is definitely one. And type 1a supernova light curves, getting them standardizable in the number of filters. I think that drives the 6 filters. So cosmology is driving the need for 6 filters. And then adding narrower filters is a proposal for after the 10-year survey, like about $1 million per filter.
I see.
So you can get together, buy your desired filter band pass, put it on, and there'll probably be narrow band. I would guess that's very likely thing to happen after 10 years.
I see.
Yeah.
Thanks for answering on the, yes, please go ahead.
Thanks. So the baseline 5, you said it was simulated how every position will be observed. So is that simulation public? Like, for example, if someone wants to know, okay, at given point at the end of 10 years, like, some patient person, end of 10 years, I want to know at a given RA deck or a given star, what will be sort of like a simulated epochs of observation so that you can do some sort of retrievals of possibilities of detecting certain signatures. So is that data set available publicly, or does the right holders have that data?
So it's definitely not proprietary. The simulations are out there and they're public. There's also software that you can use to read the specific data files, to interact with them. I forget, actually, I know where you should start. We have a technical documentation page, survey strategy. And it's .lsst.io. So that website has everything about the survey strategy, the software that you need to read the files. I assume the link to where the databases are is also in there somewhere. If you can't find it, you can email me. Yeah,
Thanks.
but it should be public, yeah.
Thanks.
I think that will close the question answer session. Thank you very much again for such a wonderful talk and introducing us to the. I invite everybody to please join us in a tea and some.
Thanks. Thank you.